Welcome back. Today we're going to look at parametric equations, which is actually very useful because traditionally we have graphed equations using two variables. So say we have this instance where we have an object being propelled in the air at an angle of 45 degrees and has an initial velocity of 48 feet per second. Well, we can show that parabolic path with this equation. But this equation does not tell us the whole story. So if we introduce a new variable, a third variable like t, which is called a parameter, we can actually describe these functions with more detail. So the parametric equation for the x would be 24 root 2 times t. The parametric equation for y, negative 16t squared plus 24 root 2t. Now we can see that on the graph, we still have the same parabola that we're used to seeing, but now we can have more detail. So the definition of a plane curve is if f and g are continuous functions of t on the interval I, then those set of ordered pairs, f of t and g of t, is plane curve C. X is described as a function of t, and y is described as a different function of t. These are the parametric equations for C, where t is the parameter. Now I really want to make sure we take emphasis here, is like I said, the parametric equations give more of a story. And so when we start plotting the points are going to be in an order of increasing values of t. And that's going to give us the orientation of the curve. This is a really interesting curve, the butterfly curve. It's a transcendental plane curve discovered by Temple Fay. And it's given with these parametric equations, which is so interesting because you have seen these already. We have sine of t and e raised to the cosine t and powers of sine and cosine. And it makes this beautiful butterfly curve. Now let's go to example 1. We're going to sketch the parametric curve. So just notice that t is defined as values between and including negative 2 and 2. So I'm going to start off with t as our values between negative 2 and 2. X equals t, and then y equals negative 2t. So we could easily fill those values in. Go ahead and graph the function and come back when you're done. The parametric equations describe a linear function between and including negative 2 and 2. For the next set of problems, we're going to eliminate the parameter. So what we want to try to do is write the parametric equation back into a rectangular equation. So the easiest steps are just to solve for t in one equation and then substitute it in the other. I want to make sure that we make a caveat here. Be careful to check the domain. So looking at A, this is going to restrict the domain. So t has to be greater than 0. If I isolate t here, I'll have to square both sides. So t will equal 1 over x squared. When I substitute into the second equation, I get y equals 2 times 1 over x squared. So the final equation would be y equals 2 over x to the 4th. But remember, we had to restrict the values for t. And I know that we're going to have to use a square root here. So I'm going to try to find values that are very small, but are perfect squares. So if I use 1/9, I use 1/4, 1, 4, and 9. So plug in 1/9, we'll get 3. And for y, we'll get 2 over 81. Plug in 1/4, and I'll get 2. And 1 over 8. For y, plug in 1, we'll get 1 and then 2. Plug in 4, we'll get 1/2 for x, and 32 for y. And for 9, we'll get 1/3 and 162 for y. So thinking of this curve, when x equals 3, it's going to be very close to 0. When x equals 2, it'll be 1/8. When x equals 1, y will be 2. And then as we get closer to 0, it's going to keep getting higher and higher and higher. So considering this curve, the range and the domain are restricted. So we know the domain will be restricted from 0 to infinity, and the range is also restricted from 0 to infinity. The utility of the parametric equations is knowing the orientation. So it's going to start on the bottom right, and as time increases, it's going to go towards the top left. So for the rectangular equation, I'm going to just make sure that I clarify that x has to be greater than 0. So for this one, we're also going to start looking at the domain restriction for t. So remember, if the square root of t plus 1 is in the denominator, then we know that t plus 1 has to be greater than 0. So t is going to be greater than -1. When we consider values for t, we should make sure that we don't include -1, but we can include values that are close. So I'll include -0.75, 0, 1, 2, and 3. All right, let's eliminate the parameter for the equation. Isolate t in the first equation, so I'll have x squared equals 1 over t plus 1. T will equal 1 minus x squared over x squared. Now we'll plug that into the second equation here. So y will equal 1 minus x squared over x squared over 1 minus x squared over x squared plus 1. All right, and that's going to simplify into 1 minus x squared. So let's graph it. Let's plug these points in. -0.75 we'll get 2 and -3. For 0 we'll get 1, 0. For 1, 0.707 and 0.5. For 2 we'll get 0.577 and 0.667 for y. And for 3 we'll get 0.5 and 0.75. Now let's sketch the equation. So at 2, it'll be at -3. At 1, it'll be 0. And then we'll start having these values increase until we get to x equals 0. It will look like half of a parabola. And again, we can see that that y-intercept is going to be 1, and it's going to be opening down. Now the orientation for this parametric is starting from the bottom right and going up to the top left. So for this rectangular equation, even though it's a parabola, we have to just make sure we clarify that the domain is going to be greater than 0. For the next set of problems, we're going to eliminate the angle parameter. So here we're given two parametric equations. X is equal to 2 times cosine theta, and y is equal to 2 times sine of theta. And we're restricting the angles from 0 to 2 pi. So let's plug in some angles here. So if we plug in 0, we're going to get 2 for x and 0 for y. At pi over 2, we'll get 0, 2. At pi, we'll get -2, 0. At 3 pi over 2, we'll get 0, -2. And back to 2 pi, we'll get 2, 0. So let's just sketch that. You can see this graph will be a circle. And with the orientation, the parametric equations describe a counterclockwise motion. So how do we get the equation of the circle from these parametric equations? Well, we can isolate cosine theta. That equals x over 2. And we can isolate sine of theta. That equals y over 2. And if you remember the Pythagorean identity, cosine squared plus sine squared will equal 1. If I substitute them in, we'll get x squared over 4 plus y squared over 4 equals 1. And we can multiply both sides by 4 to get the equation of the circle. Now let's try another one. So here we have x is going to be equal to 3 times cosine of theta, and y is equal to 4 times sine of theta. So if we plug in 0 for theta, we'll get 3 for x, 0 for y. Pi over 2, we'll get 0 for x, and 4 for y. When theta equals pi, we'll get negative 3 for x, 0 for y. At 3 pi over 2, we'll get 0 for x and negative 4 for y. And then back to 2 pi, we'll get 3 and 0. All right, let's sketch this one. You can see from the graph that these parametric equations make an ellipse. So let's figure out how to get the equation for that ellipse. Again, remember, isolate cosine of theta, that's x over 3. Isolate sine of theta, that's y over 4. And then use the Pythagorean identity. So x over 3 squared plus y over 4 squared equals 1. So the equation for our ellipse will be x squared over 9 plus y squared over 16 equals 1. With the calculator, you can change your mode from degrees to radians and the functions into parametric equations. So when you click on y equals, you'll get x1 and y1. Okay, now finding the parametric equations for a graph is actually not too bad. Now we just need to use some substitution. So if we're given that y equals 4x minus 3, and then for the first parametric equations, we know that t equals x. Well, that's easy. X equals t. We can substitute x in the equation with t. So y equals 4t minus 3. If t equals 2 minus x, we'll have to just isolate x. So x will equal 2 minus t. So y will equal 4 times 2 minus t minus 3. And we could just simplify that really fast. So y will equal 5 minus 4t. Now let's look at projectile motion. When we look at the parametric equations, we're going to use this simple formula, d equals rate times time. So we know that the velocity given with vector v is the initial speed. With angle theta, we can figure out the vector for x and the vector for y just with sine and cosine. So the vector for x will just be v times cosine theta, and then we multiply by t because we're thinking of the horizontal motion or horizontal distance. Whereas for the vertical motion, we'll have to take the acceleration of gravity into account. So we're going to have negative 1/2 times the gravity constant times t squared plus v times sine of theta times t plus the initial height. Well, a lot of cities actually have this now, but the annual pumpkin tossing contest, pumpkin chuckin', had a contestant that won the catapult competition using 2 telephone poles. So you vaulted this pumpkin at an initial height of 25 feet, that'll be a rise of 0, and an angle of 45 degrees, with an initial speed of 125 feet per second. So v will equal 125. So to write the parametric equations, well, we know that x of t will equal v times the cosine of theta times t. So that's 125 times cosine of 45 times t. And we can write that as 125 root 2 over 2t. For the vertical motion, we know that's going to equal negative 1/2 times the constant for gravity in feet, 32 feet per second squared, times t squared, plus the velocity times sine of theta t, plus the initial height. So y of t will equal negative 16t squared plus 125 sine of 45 times t plus 25. And so our equation for y will be negative 16t squared plus 125 root 2 over 2t plus 25. So those will be our parametric equations to model the pumpkin toss. Now we want to find how far the pumpkin will travel. And so remember, when we consider the parabola, the distance that it travels will be the x value, and the vertical component would equal 0. So we're looking for that horizontal distance, but we'll need to figure out the time when the vertical motion equals 0. So we can set this equation equal to 0. We can't factor it, so we'll have to use the quadratic formula. So t will equal negative 125 root 2 over 2 plus or minus 125 root 2 over 2 squared minus 4 times a times c all over 2 times a. So we can tell that the denominator is going to be negative, so we actually want to find the negative value in the numerator. So I'm going to simplify this into negative 88.388 minus the square root of 9,412.5 over negative 32. And that time will be approximately 5.79. So we can plug t now into x. What is that horizontal distance when time equals 5.79? Well, we can just plug that into the second equation, and that'll be approximately 511.77 feet. Now, another way is to eliminate the parameter. So you can isolate t and then substitute that into the second equation, but this method is probably a little bit faster. That's it for today. We'll go over any questions together in class.